All right, good. So today we are going to be talking more about multigrid and then application of multigrid in actually solving PDEs. And that includes steady state PDEs and unsteady PDEs. And all of you have worked on unsteady PDEs for project 1. And in project 2, we are actually going to be solving the same PDE as you are working in project 1, but under slightly different conditions. And these conditions would make it much more preferable to use an implicit time stepping scheme and using an iterative solution method in solving the equations that comes up with discretizing equation with implicit schemes. So this is what we are going to be talking about today. So first of all, how many of you were here last Monday? All of you? Okay. So I hope you remember the code we wrote last week on the multigrid scheme. So a multigrid scheme follows, a multigrid cycle follows something like that. So if you think of the vertical axis being how fine the grid is, okay, and on the top of the vertical level it's H, and H is the finest grid spacing, the spacing between two adjacent grids. And once you go down a level, you cosine the grid by a factor of 2, we get to a grid denominated as 2H. Grid spacing becomes twice as cos. And when we go down from here to here, what do we actually do? What do we do when we go from here to here? Yes? We cosine, but before, yeah, that's right. Before we cosine, we perform a few iterations of what we call pre-smoothing, right? And in last lecture, what we did was Jacobi or under-relaxed Jacobi iteration, right? That's been proven to be a good smoother. And what do we mean by a good smoother? Good. A good smoother reduces the high frequency component of the solution error. Solution error means the difference between the real solution, the exact solution of the linear system, and the current iterative solution. Right, so we apply smoother and then interpolate the fine grid solution down to the coarse grid solution. Okay, is that right? Do we interpolate the solution from the fine grid to the coarse grid? We don't, right? So I said something wrong. We didn't interpolate the solution at all. What we interpolated was the residual. Interpolate the residual. And why do we interpolate the residual? Because we are solving the error equation AE equal to R on the coarser grid. Okay? Okay, once we get to the coarser grid, we smooth again, we apply the smoother again to the error equation. And then we compute the residual of the error equation, right? So every time we compute the residual, it's the residual of the equation we are solving right now, which in this case is the error equation. We interpolate the residual of the error equation. And when we go to an even coarser grid, we are solving the error equation of the error equation. And when we go to the 8H grid, we are solving the error equation of the error equation of the error equation. It is a totally recursive scheme. All right? Okay, so that is when we go from fine to coarse. Now, when we go from coarse to fine, what did we do? Let's see, when we go from here, we solve the error equation of the error equation of the error equation. Yeah, there is a word for that. The interpolation from a coarse grid to fine grid is a prolongation, but let's just call it interpolation from coarse to fine. So we interpolate the error, the solution of the error equation. So we interpolate E from 8H to 4H. And then we add this error to the solution, to the smooth solution at 4H. And the smooth solution itself is the solution of the error equation of the error equation. So we interpolate the solution, we add the solution of the error equation cube to the solution of the error equation square, right? And that becomes a better solution of the error equation square. And then we interpolate it to the error equation itself and add the solution of the error equation to the solution of the error equation square. That becomes a better solution of the error equation. Then we interpolate to the original grid and add it to the solution. Then it becomes a better solution of the original linear system. All right. When we go to the code, actually the mechanism of a recursive function call makes all these a lot easier. So, for example, let's go to the code. Okay, I basically copied the multigrid function we wrote to the new folder, and we also constructed the right-hand side. In this case, I actually saved the right-hand side D as a .mat file, so we can just load it. Okay, so we have a B 1025 by 1025 matrix loaded, and let's start from a 0 solution of the same size. If I B times 0, that's 0, but the same size. All right. And so let's just remember the code a little bit. So this is pre-smoothing. This is solving the error equation on the cost grid. So this is computing the residual, interpolate the residual to the cost grid. This is the recursive call. This is calling multigrid to solve the error equation, which then calls multigrid again to solve the error equation of the error equation, which then calls multigrid again to solve the error equation cubed, which actually calls again to save the error equation to the fourth. Right? Okay, and after this, we interpolate the solution of the error equation, or approximate solution, to the fine grid. So this is the whole interpolation. These three lines are interpolation. Then we add the solution of the error equation to the original solution. And there is a post-smoothing step, just to make the solution nicer when we get out of the multigrid function. Okay, because the interpolation from cost to fine introduces what's called the interpolation error. That is actually high frequency. And the post-smoothing removes the high frequency content and makes the solution much better.